Hi, everybody. I'll get started now. Can someone verify they can hear me, please? Anybody?
Yes, we can.
Okay, thanks. Thanks very much. Okay, so I'll repeat the announcements I made last time very briefly. There are no labs this week. There'll be a quiz this evening. The details of the content of the quiz and other logistical information is on Canvas. I will have some special pre-quiz office hours today at those times, and Zoom links are on Canvas. And I'll also remind you that if your Penn State user ID starts with the letters IL through JT, you're encouraged to post questions in the chat that will be used later to determine whether or not extra credit will be given. So I encourage you to come up with good questions as I'm going. Today, what we're going to talk about is how to make mass out of energy. Answer the question if whether or not mass is conserved. Talk about why all atoms should collapse and Einstein's second major contribution. And the latter two things we may or may not get to today, but if not, definitely Tuesday. So first, I'd like to do a quick example problem on time dilation, topic which we discussed last time. And this is kind of a frightening problem. It asks, at what speed, as a fraction of the speed of light c, must 50-year-old parents travel on a rocket to and from a distant star so that they age 10 years while their 20-year-old child on Earth ages 40 years, making them the same age when the parents return? So that's a little scary to think that you might be the same age as your parents. So to do this, we're going to treat the problem in the same way we treated the problem of the person on the airplane last time, traveling from LA to New York. That person on the airplane measures the proper time, the time that's slowest, because that person has the timing device whose position doesn't change in that reference frame from the first event, the takeoff in Los Angeles, to the second event, which is the landing in New York. Likewise, in this case, the proper time is measured by the parents on the rocket. And so that's the delta tau that goes up here in the numerator. And that is given as 10 years. And we set that equal to the 40 years that the child is going to age during that time, and then just solve for this numerator here. And what you find is that the velocity is equal to an appreciable fraction, 99.65% the speed of light. So fortunately, you don't have to worry about this ever happening because we have no technology that can make large macroscopic objects move that fast. What I'd like to cover next is a new invariant quantity called the space-time interval. And just to remind you, this is the second invariant quantity. The first one that we talked about already is the speed of light. So the speed of light is invariant because it doesn't matter what reference frame you measure it in, you always measure the same value for c. So this second invariant we're going to talk about now, the space-time invariant, is a bit more complicated. It involves the speed of light, but it's more geometrical. And by way of analogy, consider the following invariant in 3 dimensions, namely the distance between 2 points. So that's shown by this figure over on the right, where we measure the distance d between 2 points labeled 1 and 2 in the figure. And we do it on axes that are oriented, in the normal way you might draw them, perpendicular to one another and labeled as x and y. And the distance between points 1 and 2 is just given by, as you would expect, delta x, which is x2 minus x1 squared, plus delta y squared, square root of that whole quantity. And that gives you the distance d. So now what happens if you have the axes, x and y, looking like this, and you rotate them? And you still have, you know, this is, say this white pen here represents the distance d, where one point is down here and the other point is up here. What happens if I rotate the axes? So that's what I've done down here. We now have the axes x prime and y prime. What happens to that distance d? And the obvious answer is nothing. We still measure the exact same length for d. It's an invariant in 3 dimensions. In this case, we're just looking at 2 dimensions, but you can imagine if there was a 3rd dimension, the same thing would hold. And we're here, delta x prime and delta y prime are not going to be individually equal to delta x and delta y. If we compare delta x squared plus delta y squared to delta x prime squared plus delta y squared, we will find that those are equal. So this is an example of an invariant in 3 dimensions. The invariant that's relevant for relativistic scenarios is called the space-time interval, and it works in 4 dimensions, the 3 spatial dimensions plus the time dimension. And the invariant quantity is written like this. So it's just s squared equals c squared delta t squared minus delta x squared minus delta y squared minus delta z squared. And this is derived in the text. I'm not going to derive it here. And we're going to use the simpler version where we just drop the y and z coordinates in order to have an expression that looks like this. So the delta y and delta z are, you know, implied, but it's just simpler to write it down with just one of the dimensions. So what this tells us is that for any given pair of events, like one event might be this firecracker explodes at time t1 at position x1, and this one explodes at time t2 at position x2. Those are 2 firecrackers explode, okay, at 2 different positions at 2 different times. If we calculate c squared delta t squared minus delta x squared for someone who is just standing on the ground watching these 2 things happen, or if we calculate this s squared if we're moving past those 2 firecrackers as they blow up, you know, we're driving by in a car, we will measure the same thing for s squared in both cases. There's a pretty good example in the textbook of this, how to use this to the space-time invariant, space-time interval to simplify a measurement of something that would be pretty hard to do otherwise. Unfortunately, I'm not using it here because it relies on some knowledge of something called length contraction, which is related to time dilation. It's a relativistic effect, but we're not going to cover it in this course. It's not so hard to understand. You can read through that section, and then you can understand this example even if you don't understand length contraction. But here instead is a partial justification. Let's consider a photon traveling past, and we're in 2 different reference frames, inertial reference frames, S and S prime. Or one of us is in one of those frames and someone else is in S prime. So what will we measure if we're in reference frame S? Well, what we would measure is this quantity here for that photon. The photon is moving with speed c. So it's going to move you know, a distance delta x that's equal to c times delta t. Time between the 2 measurements that you make and, you know, the distance it travels are going to be related to its velocity, and its velocity is c. So the difference of these 2 quantities is going to be 0. If you're in a different reference frame, if you're flying by, you know, in a spaceship going at 0.9 the speed of light and looking at this same photon, you will measure exactly the same thing, because remember, independent of what reference frame you're in, you always measure the speed of light to be c. So this stays the same in this equation. And you measure a different delta t, and a different delta x, so delta t prime and delta x prime. You measure a different time between these two events happening, and you measure that they happen at two different places than the person who was not in the spaceship. But when you form this quantity, c delta t prime squared minus delta x prime squared, you will also measure 0. So if you're measuring the space-time interval for a photon, it doesn't matter which inertial frame you're in, you will always measure the same thing. In this case, the same thing will always be 0. So in this case, the invariant is 0, the number 0. So let's multiply this space-time interval by something which we can plausibly argue is a constant, namely the mass of the particle. So if it's traveling through vacuum, that mass is not going to change. And delta tau, which is the time, the proper time, I should say. So it's the time measured in that particle's reference frame. And if we do that, and we multiply this invariant, c delta t squared minus delta x squared, by that quantity, what we get is that this expression is invariant. So because c delta t squared minus delta x squared is an invariant, if we just multiply it by a constant, the equation that results is also going to be an invariant. And the equation that we get is gamma mc quantity squared minus p squared, the momentum, equals some constant. And then just below that, it's rewritten, but now with an added c squared factor multiplied through. So nothing has changed from this equation to this equation, just multiplied by another constant. This is the traditional way that it's written, so that's why I put that there. Okay, so I've written that gamma mc squared squared minus pc squared is equal to an invariant. The question is, what is that invariant? I mean, if we can find out what that invariant is, then it'll be true regardless of what reference frame we use. That's the definition of an invariant. So is there a way we can find what this invariant is? And one thing we can do to make our lives easier is choose a convenient reference frame in which to evaluate the stuff on the left-hand side of this equation. So what's a convenient reference frame to choose? So I remind you that what I'm asking is, if we have a particle, say, moving around, and we want to choose to figure out what this invariant quantity is, we can sort of, here's my reference frame, and we have a particle moving by. I can use that reference frame, or another alternative would be to use a reference frame that moves with the particle. Or you could make your life really difficult and choose a reference frame that's moving in the opposite direction of the particle. Okay? You have an infinite number of choices, but someone has written down the correct answer in there. You would want to choose a reference frame where p is equal to 0. So that's the reference frame that moves along with the particle. And then if you're in that reference frame looking at the particle, just like if you're in the car looking at the bicycle and the problem we did when we were talking about simultaneity, if you move at the same speed as the bicycle and you're looking at the bicycle out your window, the bicycle as it appears or doesn't have any velocity with respect to you. The velocity of that bicycle with respect to the car, if your velocities are matched, is 0. Right? The bicycle doesn't look like it's moving. Of course, you can tell it's moving because you can see all the ground moving by. But if you were out in space in your car and you were right alongside a bicycle and you looked out, you wouldn't be able to tell that either of you were moving relative to some faraway planet. Okay, you would look out and say, oh, we're both at rest with one another. That bicycle has 0 velocity in my reference frame. Okay, so that was a long-winded discussion there. But what I want to say is the most convenient reference frame to choose is one where we can set the momentum equal to 0. And that's the reference frame that's moving at the same velocity as the particle itself, in which case the velocity of the particle in that reference frame is also 0. If the momentum is 0, so is the velocity. And that means that gamma will be equal to 1. So in that convenient reference frame, both p equals 0 and gamma equals 1. And then if we then solve, we put in gamma equals 1 here, and we set p equals 0 here, what we get is that the invariant quantity is just mc squared squared. So here we see the famous mc squared term coming up. And what this means is that in any reference frame that we choose to use, so S prime, S double prime, S triple prime, whatever, we measure mc squared squared for this invariant. So when we measure the velocity and the momentum of the particle, and we put them into this formula here, whether we're in one reference frame or we're in another reference frame, so this might be the S frame and the S prime frame, if we form that difference between those two quantities, we will get the same thing in both cases, in all cases. So if you look at this equation, you can see here that there's momentum appears, and we know momentum is conserved. And also this particle is all by itself, so its mass is not going to change. And of course, the speed of light is a constant. So we've got constants everywhere. So the question is, except for here, what is this quantity? What is it related to? Is it something that's also, constant? So we need to figure out, or is it conserved, I should say, as opposed to constant? Because we know these are constants here. This is conserved. So what's going on here? So you might have guessed that it's related to energy because it's got that mc squared in it, and we know Einstein's famous equation is E equals mc squared. So let's show it, in fact, that it is related to energy. And to do that, we're going to use the binomial approximation to write down an approximate expression for gamma mc squared. So remember that gamma is just defined as square root of 1 minus beta squared, and beta is just the velocity as a fraction of the speed of light. And also remember that the binomial approximation tells you that 1 plus x to the alpha is approximately to 1 plus alpha x if x is small compared to 1. And I think also alpha needs to be small as well. Okay, so we satisfy those conditions if the particle is not moving super fast. And what we get if we write out several of the terms in the binomial approximation is you get this expression here. The first term is 1, and then we have a 1/2 u squared over c squared. Then the next term is 3/4 u to the 4th over c to the 4th, and it's all multiplied by mc squared. And we can multiply everything across, and you see we have an mc squared and then a 1/2 mu squared. Remember, u is the velocity of the particle in a particular rest frame, particular inertial frame, I should say, plus additional terms. So this first term here, this mc squared term, is new. It's the rest energy of the particle. It's energy that's associated strictly with the mass itself. And this is not something that people had considered before. The second term, of course, looks very much like kinetic energy, 1/2 mv squared. Now, instead of v, we're using the symbol u, but it's the same thing. And then there are additional terms here that I'm going to argue are small corrections. Why can I argue that? Someone want to answer in the chat? What makes the remaining terms small corrections?
Is it because their value is going to be very small compared to the other terms within the equation?
Yeah, so the value is going to be small, and as someone else mentioned, it's a power series and it's large magnitudes, the large magnitude of c, and the speed itself, u, is slow. In other words, this term here, for example, is the one we kept, and there, if you're moving at 10% of the speed of light, that's u squared over c squared, gives you 0.1 squared or 0.01. So this term is small compared to the rest mass. But if you look at this term here, then you have a u to the fourth over c to the fourth. So 0.1 to the fourth is a much smaller number. So it's down obviously by a factor of 100 compared to the previous term. So if u over c is small, as we go out further and further in this power series, we're going to have higher and higher powers of u over c. And if u over c is a small number, the higher the powers go, the less and less relevant those additional terms are going to be. So we're just going to ignore, or we can ignore those terms in general. All right, so we can define the total energy as E equals gamma mc squared, where that total energy is made up of two parts, the rest mass energy and the kinetic energy, written as E0 plus K. And this kinetic energy is dominated by the 1/2 mu squared, and there are then these small correction terms. So this gives us the famous Einstein expression, energy equals mc squared, but now we know there's a little bit of a nuance there. This is the rest mass energy of the particle, and its kinetic energy is given by gamma minus 1 times mc squared, or gamma minus 1 times E naught. So we can plug these new variables or terms into our invariant. So here was the invariant from a few slides ago. And we get this new expression down here. So the total energy squared minus the momentum times the speed of light squared is equal to the rest mass energy squared. And this is always the case, independent of what reference frame you're using to measure the total energy and the momentum. If you take the difference of E squared minus PC squared, you will always get the same value independent of what reference frame you make the measurement to. That's a definition of an invariant. Okay, as an aside, I'd just like to mention when we need to account for relativistic effects. And to evaluate this, there's no definitive answer, I should say, from the outset. But to evaluate this, we'll write down the expression for the kinetic energy, which is gamma minus 1 times mc squared, and use the binomial approximation again to see what it simplifies to, provided that beta is small. So we just rewrite gamma minus 1 like that, remembering what gamma is equal to. And then this term here, we're going to use the binomial approximation to write as this. So with it written that way, you can see that you get 1/2 mv squared as the kinetic energy, which is the classical expression for the kinetic energy. So this is valid provided that beta is small. So in other words, as long as beta is sufficiently small that making this approximation doesn't introduce large errors or inaccuracies, you can treat the system non-relativistically. All right, let's try applying some of this stuff. So I want you to think about this concept question here, which asks, imagine you have two mass lowercase m particles heading towards one another with equal and opposite velocities, u and plus u and minus u. So here are the two particles, my fists, and they're coming together and they smash together inelastically. So before the collision, they had some kinetic energy each. And then after the collision, there's no kinetic energy. And the total mass of the two particles together is capital M. So the key thing to think about here is there was kinetic energy initially, and and two masses, little m on one side, little m on the other, total mass of 2m. And then they collide. They have a total mass, capital M now, but no kinetic energy. So how are the final total mass, capital M, and the individual masses, little m, related? If you think about where that initial kinetic energy could have gone, it says kinetic energy in the beginning, and then the two particles collide together inelastically, and then there's no longer any kinetic energy in the final state. So someone asked in the chat if kinetic energy is always less than rest mass. It is typically much less, but it doesn't have to be. All right, so get your answers in, please. For subatomic particles, you can often have the kinetic energy larger than the rest mass. For macroscopic particles, you can't, or at least we don't know how to do it. All right, so most people answered C, but there was a pretty large fraction that said B, that the mass at the end is equal to twice the mass at the beginning. So C is the correct answer, and we'll do this quantitatively in a second, but qualitatively, just think about what we had in the initial state. We had two little mass m, so that's my fists, and they had some kinetic energy before they collided. After they collide, they're stuck together. There's no momentum anymore. There's no kinetic energy anymore. So, well, I should just say there's no energy. There's zero net momentum here, zero net momentum after. There was kinetic energy here, and there's no kinetic energy now. So that kinetic energy had to go somewhere. And it goes into the mass of the larger final state particle. The two particles mushed together now have a mass that's larger than twice the individual masses of the particles. And we can do this quantitatively as follows. So this is exactly the same question as before. What we're going to do now is write down the initial and final energies and apply energy conservation and see what it tells us. So here's the initial energy. It's 2 times gamma mc squared. So remember, the total energy of a particle is just gamma mc squared. We have 2 of these particles, the 2 coming towards each other. So they each have gamma mc squared in total energy. So the total initial energy is just the sum, gamma mc squared plus gamma mc squared. And that can be rewritten, just expanding out, writing out what the gamma is as 1 over the square root of 1 minus u squared over c squared. The final energy, these 2 particles have come together. There is now no longer any velocity, no longer any kinetic energy, but there is a mass, capital M. So the total energy in the final state is just capital MC squared. There's only rest mass energy because there's no motion. But energy is still conserved even when things are moving relativistically. So we set these 2 things equal to one another. And that gives us this expression here, which tells us quite clearly that the capital M is actually going to be larger, certainly not equal to, twice the lowercase m. And it's related by this square root of 1 minus u squared over c squared factor in the denominator underneath the 2m. And what this tells us is that mass is not a conserved quantity. Mass and energy can flow back and forth to one another. In this case, energy is flowing into mass because we had energy in the beginning when the 2 particles are coming together, and then afterwards we have more mass than we started out with because some of that energy, or all of that energy, got converted into mass. Now, of course, some of it gets converted into sound and heat and all that those are other forms of energy. So some energy actually escapes. But if you do this with subatomic particles, where you don't have sound and heat coming out, you do find that two lighter particles coming together can form a new particle that has a larger mass than either of the two constituents that came in, because some of the kinetic energy, or all I should say, in the case of subatomic particles, gets converted into mass. Nuclear reactors that use fission go in the opposite direction. They basically convert mass into energy by having particles, nuclei split and fission, and they fission into two smaller nuclei whose summed masses are less than the initial mass of the parent nucleus, and that difference in mass is released as energy, which then like heats up some water or something and turns a turbine and makes electricity. Okay, so that's the end of our discussion of relativity. What we're going to talk about next is closely related in the sense that just like relativity caused a lot of head scratching back when it was first discovered, there were other things that scientists were measuring that were also causing a lot of head scratching. And ultimately this led to the discovery of quantum mechanics and the advent of what we now call modern physics. So relativity is one of the first cracks in the picture that people had drawn, from like 1600 up to 1900, starting with Newton and then with Maxwell describing electromagnetism. For a while there, physicists thought, well, we have everything explained, we can just go home, we're done, okay, all finished. But then Einstein came along and said, well, wait a minute, we don't quite understand how things behave when they're moving really fast. And other experimentalists were measuring things that also could not be explained with Newtonian mechanics and or Maxwellian electromagnetism. So some of these things included the emission and absorption of light. And one of the ways you can get objects to emit light is by heating them up. And for reasons that were unclear, if you took a lump of coal and a lump of iron and you heated them up to the same temperature, they emitted exactly the same radiation patterns. And what that means is the same spectrum of light was produced by them. And by spectrum, I mean, if you look at, just drawing a little plot here, what the energy was as a function of, say, wavelength, you would see something like this. Actually, this is probably 1 over wavelength or frequency. That's a better way to put it. So at the shorter wavelengths, at the higher energies, there was less energy, and at the longer wavelengths, there was high energy. But this depended, it turned out, on the temperature and not on the material, which people couldn't really understand. Also, when they looked at gases instead of solids, instead of seeing a continuous spectrum, which is what's shown here, what they saw instead were some discrete lines. So if I look at energy versus wavelength, they would see a few discrete lines whenever they excited or heated up gaseous atoms and looked at what was coming out. So can you think of actually ways that you might be able to measure those discrete spectra? And I'll let you think about that while I continue. So at the same time, people were finding that atoms had substructure. Namely, that there were these smaller particles that looked like they made up atoms, although it was unclear how they made up atoms. So these were, as you know, electrons, protons, and neutrons. It took a while to figure out how these were arranged within an atom. We kind of take it for granted now, but they were very much groping in the dark back then. And even once the arrangement became clear, classical physics predicted that neither, the nucleus, which had a bunch of positive charges in it, and so therefore, should just fly apart, and atoms themselves should not be stable. But they were, of course, most of them anyway. So it was a big puzzle as to why that was the case. So in the next few slides, we're going to explore these observations and discuss the implications. So this is going to be kind of a whirlwind tour of all the problems that people were seeing that eventually gave rise to quantum mechanics. So first, let's talk about discrete spectra. So as I mentioned in the previous slide, gases were shown to emit and absorb at particular fixed wavelengths. And this was first discovered by Faraday, who was sending electric currents through gases, and he found that they were emitting discrete spectra. So has anyone thought of what kind of device they might have used to determine that the spectra that were coming out were discrete? I mean, if you send an electric current through a gas and it glows, blue, just by looking at it with your eye, you won't be able to tell if that's because it's sending out one wavelength or if there's just like a smear and it's kind of mostly blue. It's tilted towards the blue. So someone suggested a prism, possibly. Yes, diffraction grating is what they used. So if you send this light through a diffraction grating and it's a single wavelength or a few discrete wavelengths, you'll get a few discrete lines on a screen that projects the image from the diffraction grating. In any case, this behavior could not be explained with classical physics. They did not know why the spectra were discrete. There was an interesting clue that came from a Swiss school teacher named Balmer, who was pretty good at recognizing numerical patterns and also must have been really patient, because back in the days when you didn't have calculators available, what he did was he looked at the wavelengths that had been measured for hydrogen, excited hydrogen. And there were like 7 or 8 of these wavelengths, maybe only 3 or 4. And then he was able to show, after I'm sure a lot of trial and error, that they obeyed this expression. But it would take sort of nearly 30 years to figure out why this was the case. So it's one thing to show that things have a numerical pattern, but if you don't know the underlying reason, then showing that it has that pattern is basically an exercise in numerology. But in this case, it really drove people because it matched so well. There had to be an underlying reason why it described the wavelengths and their positions so well. And when physicists were eventually able to predict from a fundamental equation this expression, that was a major triumph for quantum mechanics. So meanwhile, there was progress that was being made with experimental devices that allowed the discovery of some of the key constituents of the atom. Namely, one of them is the electron. And this was done using a device called a vacuum tube, which is basically an enclosed glass envelope around what's mostly an evacuated space. So there isn't any air inside, or very little. And the advantage to this is because electrons, for example, are very interactive. If I release an electron right here in the air in front of me, it won't travel very far at all before it bangs into something and gets absorbed. So you really want to remove as much air as possible so that you can observe the behavior of these particles. So this technology of making these vacuum tubes helped in this regard. And what they used to do is they could also put metal electrodes, inside the vacuum tube and control them from the outside. So there was a seal, right there where the wire came in. And at the cathode end, indicated on the left here, they would generally do 2 things. They would place a negative voltage on it and they would heat it up. At the far end, this collecting electrode, also called the anode, they would set this at a high positive voltage. So we have a negative voltage on the left and a positive voltage on the right. And then we make the temperature really hot on the cathode on the left-hand side. And when you make it hot, some of the electrons get enough energy that they jump off of this at the surface. And when they do that, they immediately see this negative voltage behind them and this positive voltage in front of them, and they start racing from left to right. And those are indicated by this label, cathode rays, which are now known to be electrons. And they're collimated through a hole here in order to make sure you're just getting ones that are going in straight lines, because that makes it a little easier to make the measurement. You don't have as much noise to worry about. So I have a video of one of these in action. So let me get that up here. So I hope you can see that. On the left-hand side of this still image is the cathode. So that's where heat is going to be applied and a negative voltage is going to be applied. And then on the far right-hand side is the anode, which is going to be at a positive voltage to attract the electrons that are going from left to right. And then in the middle, just to the left of the glowing green, is the collimator, which you can't really see, and also an additional feature, 2 plates, just like capacitor plates, where an electric field could be applied. And I'll mention what that's for in a minute. And then you see this green glow. That's from the electrons that are hitting a fluorescent screen that's also placed inside of this particular vacuum tube. And so you see the electrons traveling from left to right. And one thing that was observed is if you brought a magnetic field in close to this, and you can see there's like a bar magnet at the end of that metal arm that someone's putting in there. For some reason, they don't want to use their hand. That causes the electrons to change their paths. It bends them. So it was initially, unclear what was causing the glowing that they were seeing. And they actually did things a little differently from what I just showed you. So if we take this cathode ray tube up on top here and move the sensor vertically, the collecting electrode, and then apply a magnetic field, what was found was that only certain magnetic field strengths gave a current that would be produced by this device whenever an electron from the cathode would come out and hit the collecting electrode, the anode. So if the magnetic field wasn't present, then you would get this trajectory here. If the magnetic field was too strong, you get this trajectory, and you wouldn't see a current. If you had the magnetic field set just right, then lots and lots of electrons from the cathode would end up being collected at the collecting electrode, and you would measure a current. So this was evidence that whatever was moving from the cathode to the anode was negatively charged. And by the way, if you're reading this text here, I talk about the glass glowing, and that's what would happen if these cathode rays just sort of hit the glass, like this one would have done over here, and didn't, weren't collected on the collecting electrode. So another experimenter, Thomson, went a step further. He had even better technology for these vacuum tubes. So the technology was driving these discoveries. What he did was he used a tube more like the one I showed you in the video, which allowed him to apply an electric field as well as a magnetic field. And he was able to use the fact that if you have crossed electric and magnetic fields, then a particle that's going perpendicular to those two crossed electric and magnetic fields will only make it through undeflected if its velocity satisfies V equals E over B. And this, I hope, is something you saw in your electromagnetism course. You basically set the magnetic force equal to the electric force, and that way those two forces cancel each other and there's no net deflection. So you can use the electric and magnetic field strengths to select velocities of the particles that are going through those crossed E and B fields. And this can then in turn be used to measure the charge to mass ratio of the particle by using this expression here. So if you know the radius of curvature, after you've selected the velocity, if you apply a B field and you see it curve with some radius of curvature, you can then measure Q over M. And what was determined was that Q over M was large, which suggested that the mass had to be pretty small. And then a little while later, someone figured out a way to measure the charge directly. And it was measured it was known to be small, but it was now the exact value was known, 1.6 10 to the minus 19. And from that, you could estimate what the mass of the electron was, basically 10 to the minus 30 kilograms. So given that he had discovered electrons and he knew that electrons were constituents of atoms, he proposed the first model of the atom. So Thomson figured that since the electrons were probably light, it was probably the positive stuff that was making much of the mass. And so what he did was he came up with this model, which he called the plum pudding model, because they didn't have grilled stickies back then. It involved sort of a large amorphous blob of positive charge, embedded in which were these negative electrons. And we knew what the size of these atoms were back then. People then started trying to probe whether this model was right or not, using some rays that were discovered in around 1900 to be emitted from uranium crystals. These rays were alpha particles, which consist of a helium nucleus, so 2 protons and 2 neutrons together. So that's just a doubly ionized helium nucleus. And in particular, a person named Ernest Rutherford started studying them. And he found that one of the emitted rays, he discovered that it was a helium nucleus, this alpha particle. And he started using them to probe how different materials behaved by using setups like this one shown on the right. He would basically take the radioactive source and send it through a bunch of collimators, so he had a nice straight line of particles coming out, over here. And then he would put something in the way, like in this case, a gold foil, and see what would happen to these particles as they went through the gold foil. And what he was expecting, based on the plum pudding model, was that there would be at most small deflections of these charged alpha particles as they went through the gold foil. And the way he would measure that is by looking to see when there would be flashes of light whenever an alpha particle would hit this zinc sulfide screen. And what he was expecting to see, if this is a view of the zinc sulfide screen, he was expecting to see a whole bunch of dots right in the center, maybe occasionally a few on the outside, but mostly there'd be a big blob right in the middle because there'd be very minimal deflection of these alpha particles going through the gold foil. And just as an aside, this is just one way to detect radiation. There are other ways as well. For example, a Geiger counter is another way. And let me just briefly explain how a Geiger counter works, because you have all the knowledge you need in order to build one of these, should you be so inclined, and certainly you can understand how they work. The basic idea is you have a metal anode shown here in the center of a tube, just filled with air, and the tube is metal. The outer part of the metal is, the outer part of the tube is also metal and conducting. And you connect the anode, the inner wire here, to a high positive voltage, and the cathode, the outer part, to ground. And then if a charged particle comes through the central region of your Geiger counter, or any kind of ionizing radiation, it will cause some of the electrons in the gas inside of the tube to be separated from their parent atoms, forming ions and electrons. And then those electrons will suddenly see, should I go back to my parent atom, or should I go towards this plus 500 volt DC anode? And they will, 9 times out of 10 choose the anode because it's a huge positive voltage and electrons are negatively charged. So they start racing towards the anode. In the process, they bang into other atoms, causing more electrons to be freed. And eventually you get this gigantic avalanche of electrons that hits the anode essentially all at the same time, producing a pulse, an electrical pulse that you can then detect. And the clicking noise that you hear whenever someone shows you a Geiger counter, or if you look up on the web, is the conversion of this electrical pulse into sound. If the voltage is high enough, it can also be the result of basically miniature lightning inside of the Geiger tube. So just to wrap up, to be complete, what Rutherford did was he decided to look if any of the alphas got emitted at large angles. And he was expecting to see none, right? Because the plum pudding model should see 0. But he took his apparatus and he moved it at some large angles to see what happens. And he saw some alpha particles being bounced back. And it's an interesting quote from him. He said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you." So this is an example of how you should not just allow what you think is going to happen in an experiment to dictate how you run the experiment. Because he could very well have stopped after sending these alpha particles through the foil and never found that a bunch of them were bouncing backwards, which they never should have done if the plum pudding model had been correct. And so what he was able to conclude is that in reality, what we really have is something where there's a cloud of electrons and there's a really hard and massive inner nucleus. Okay, with that, I'll stop. Sorry, I went a little bit over, and talk to you next time. Remember, there's special office hours this afternoon in advance of tonight's quiz. Thanks, everyone.
Sir, can I ask a question?
Yeah, just a second.
Yeah.
Yeah, go ahead.
So what is absolute time? Basically simultaneity in that there was a time, right? Tau basically. So we need to be like at a single place, like we cannot move basically. But what was that? I actually got confused with that. So if you can explain.
So are you referring to proper time?
Yeah, proper time, sorry.
Yeah, so proper time is the time that's measured by a clock that is basically at the same position for the two events that the clock is measuring the time interval of.
Okay, so in the previous class, like there was a rail thing where there was Peggy and Ryan.
Right.
Peggy was basically in the platform that was moving with some velocity. Ryan was standing on the platform, okay, away from it. So which one, which part will have proper time, Ryan or Peggy?
So the two events are the explosion of the firecrackers. If Peggy is measuring the time between those two events, she will, let me think. So I want to say she will measure the shortest time between those events. Because she's measuring, she has a clock, and she measures it, and when the first pulse arrives, and then, you know, when the second pulse arrives, she measures the time difference between those two. And that's the proper time.
So, but Ryan is actually measuring it as 0, right?
Yeah, that's why I'm scratching my head here.
I basically asked you this question due to this reason only.
Let me think about this. It's a good question. Top of my head, I don't know the answer, but as usual with relativity, you need to think of things in just the right way. And if you don't, you can get pretty messed up. I'll make a note of this, and I will try to provide an answer as soon as I figure it out.
So I have one more question, if time permits.
Yes.
This is basically about Gaussian transformation.
Yep.
So I was doing the calculations as such, like what we actually do in Newtonian mechanics of relative velocity. V prime s, Vs prime s is equal to velocity of s prime minus velocity of s. Correct?
Well, the Galilean transformations are given in the textbook, right? It's like x equals x prime minus vt, I think. Or
So,
x, sorry. Is that what you're asking about? Transformations?
Yeah, I actually messed up with plus and minus. I was taking up like, you need to find x prime. The value was x minus vt.
That's
but
right.
What I was solving was I was getting like x plus vt. So I was a bit confused about that.
So what's your question?
I was solving it through like relative velocity vs prime minus vs is equal to the relative velocity if we take the vs as s as the reference frame. So
yeah, I'm sorry, I don't understand your question. Maybe you should send it to me in an email or post it to Piazza. I could try to understand it there.
Okay, so I will send her an email then.
Okay, yeah. Better to put it on Piazza if you can. Yeah, sorry.
Okay, right. Thank you, sir.
You're welcome. Any other questions? Okay, bye-bye, everyone.